Continuing on with our discussion of some preliminary issues as to do with communication systems, we'll be talking about the waveforms or some particular aspects of the waveforms which might be used for the transmission of digital data. So the last time we discussed the difference between PCM versus PAM, so that's pulse-coded modulation as opposed to pulse amplitude modulation, as being two choices. We can think of it for the waveforms. We looked at square waves, but we had this basic concept of multi-level versus two-level. So pulse-coded modulation is a binary transmission. There's two levels, and it's a faster, wider bandwidth solution than PAM. So if we compare these two, pulse amplitude modulation exploits multi-level transmission. So there are many voltage levels, for instance, which could be used. And this is a slower, narrower bandwidth solution. So two fundamental choices how we might attack the problem. Sending bits or sending symbols in the case of pulse-coded versus pulse amplitude modulation. And now to this discussion, we're going to be talking about line codes, and in particular, I want to draw your attention to two sort of fundamental choices, RZ and NRZ. So we'll be looking at line codes, many varieties. I'll point out the differences and motivate why there are so many varieties. But the real point of this discussion is to bring your attention to these two RZ and NRZ. So these are PAM, PCM, these are very common language vocabulary you'll see in digital communication, as is RZ and NRZ. So I want to make sure that I took the time to highlight these choices to you. So RZ means return to zero. That means that there's some sort of quiet time when I'm at zero voltage or zero transmission, which happens between every bit or symbol. So let's move on to some idea here. So let's consider PCM, so baseband transmission of pulse-coded modulation. So in this case, it's quite similar. We're talking about the bit duration, the time of a bit, which we see right here. And if we were going to be transmitting data which is coded, for instance, the code word might be 4, if there were 4 bits of resolution in our quantizer or whatever. But what we're looking at now is what's happening inside of this bit interval. So here I'm showing two ideas about what we might do as a choice for the PCM waveforms. For instance, in this illustration, I have some subset of the complete bit interval which I'm using for my actual transmission of my waveform. So although I have capital T as my total time allotted for a bit, I'm only using T prime here, something much smaller, where I'm transmitting my waveform. And in here, we look for a logical a voltage 0 and some other higher voltage level. And this is a very short pulse of some level. Now, here is another example of how I might choose to send that PCM waveform. Suppose I did 2 levels, so instead of logical, there would be a logical 0, but it would be a negative voltage, so this is sort of differential type of voltage. That would be another solution. So it's still binary. I could assign this a logic 1, this is a logic 0. And in this case, I'm occupying the whole time of the bit. So you might think, well, what would be a reason to want to go with occupying the whole bit time? And well, I can go back again to my Fourier analysis and say, well, if I try and make this pulse shorter, that means it's going to occupy more bandwidth, and perhaps bandwidth is a quantity that I don't want to waste, and so maybe I would prefer to go this. So we can already see that there are many choices we can make. These examples are all square waves, but I could have used some other shape, but there would still be this fundamental choice. Whatever shape I use, rectangular or otherwise, do I want to use the whole bit interval or do I not want to? Do I want to have bi-level signaling or do I want to have 0 and as one of the choices? So this is what line codes are about. It's not about the shape of the waveform, but how we exploit that waveform. And again, I wanted to point out in particular the return to 0 in the NRZ, so we can have bipolar return to 0. So normally we would have a plus and a positive and a negative voltage, and because it's a return to 0, inside of the bit time, we're stopping halfway and doing a reset to 0. And then if the next bit is supposed to be a logical 0, we'll put a negative voltage, but halfway through again, we're going to reset to 0. So this is quite clearly a return to 0. Now here's a unipolar return to 0, and it looks a little different, but really it's the same concept. Here is the logical 1, I have a positive voltage, I return to 0. For the next one, my logical bit is 0, and so I'm just staying at this 0 voltage. But one is unipolar, one bipolar, which is why they look different, but the idea of the return to 0. Now here's a non-return to 0, NRZ, and we can see that here we have our logical, and here's the bit sequence that's being transmitted. Now we can see it up at the top. Logical 1 plus V, logical 0 minus V, and there's no return to 0. Now there's a couple of varieties that I can use for NRZ, and it's described in the book. I won't go into them, but there is sort of like what a 1 or the 0 could be an indication of a transition or not a transition. So completely different way of looking at it. For instance, in this case, if we have a logical 0, that means that I would continue with wherever I am. So I had a 1 level, which was a positive V. The next bit was a 0, and I decide it's constant, so I don't change it. Now the next one is a logical 1, so I toggle. If it was a plus V, I go to minus V. And now here I am at 1, and if the next one is a 1, now I'm going to go into a toggle and toggle to the other value. So you can see it looks quite different, and here we can just change which one is the toggle bit and which one is the constant bit. So they look quite different, but their impact of this choice is changing the actual voltage signal that I am transmitting. So let's look at some implications of the choices about which line code I'm going to use. Let's look at this unipolar return to 0. Since I'm using unipolar, that means that there's 0 voltage, there's 0 transmittance. It's like I'm not sending any information, no signal during this time, which means that there's going to be no energy received at the receiver. So maybe I'm going to have trouble maintaining synchronization, maintaining lock on some estimates. I might have to do a phase or frequency or something else going on. So this is one implication of the choice that I make. Here in the NRZ S, we see that there are not many transitions. I guess same for M. Both of these would be something where we're only toggling on half the time, because only half the bits would involve a toggle. Now in those, there are some other possibilities I can make. In this case, we're looking at different, here is an example of the narrower pulse than what is needed. We have some other choices where we split the bit interval into 2 pieces. Now, why would we want to do this? Well, one reason is if we're forcing a toggle at every bit interval, you would get more transitions. And sometimes transitions are good for locking onto signals. It's easy to see what's going on. So this is one of the reasons that there are so many choices, depending on what are the impairments or the imperfections in the non-ideal components you're using. So that is why we have so many line codes that we can choose from, is to be able to have lots of choices depending on the situation we're addressing. Now, if I took these line codes and I said, well, I see what the transitions look like, but if I take a random sequence and I do the Fourier transform of that sequence and I look at what is the frequency content, and depending on which one of the line codes I use, I will get very different power spectral densities. I will get some for NRZ where there is a lot of low frequency content. Others, there could be choices where there's no DC and different applications, different kinds of components. These may be attributes that that are desirable. So, for instance, if there is a DC component, that means you may want one if you want AC coupling. If you want to be sure that your DC is always 0, you might make a different choice. Clock recovery. If your clock recovery circuit is challenged, if you need frequent transitions in order to do good clock recovery, maybe you'd want to return to 0. Maybe you need guaranteed transitions because you'll lose lock on your synchronizations if there's too long a sequence of no transitions. Maybe it's for error detection, that you know that transitions should happen at a certain point, so there's sort of some way of checking what the waveform looks like. Should you be more bandwidth efficient? For instance, non-return to 0 uses less bandwidth than the return to 0. So all kinds of reasons. So a variety of line codes, different behaviors, which allows us to address challenges that we want in any given system. And I'll recall, I make one recall before we end this discussion, is that the reasons we have lots of choices is because what makes a good communication link is not simple. We may want to be power efficient. We may want to be spectrally efficient. We may want to use less bandwidth, or we may want to use cheap components. We might want something that's robust because I have a very cheap clock signal, and maybe spectral efficiency. I'm translating my data so slowly. So I always return to this idea of being 3 criteria that are used to evaluate how good the communications link is. And there's always a trade-off in these. I can't get something that's perfect in all 3 criteria. So what I'm going to do is, in any sweet spot, I'm going to pick. And line codes are one of the things that are going to let me balance off, trade off what I want to achieve in terms of these 3 different criteria.